Hello everyone, welcome back. We're going to continue our discussion on filters, and this time we're going to cover bandpass and band reject filters. So let's start with a simple case of a bandpass filter. This is actually a circuit that should be very familiar to you. This is basically the series RLC circuit. The only difference is that we define input and output in a certain way that is going to give us the functionality that we are trying to achieve. So let's start with calculating the transfer function HS, which again you can either do circuit analysis, figure it out, or just use the voltage divider equation, which goes like this: impedance divided by the total impedance. Impedance of resistor divided by the total impedance, which would be R divided by R plus 1 over CS plus LS. So now I multiply both top and the bottom by CS, so that would be RCS divided by 1 plus RCS plus LCS to the power of 2. So now I replace S with j omega, so H j omega would be RC omega j divided by 1 minus LC omega to the power of 2 plus RC omega j. This happened because when your S here is j omega, j to the power of 2 is minus 1 and then omega 2. So this is minus LC omega 2 is a result of replacing S with j omega in this last term. I rearranged it because this part of the denominator is now your real component and this part is your imaginary component. Now with that I can calculate either hj omega, magnitude of hj omega. So magnitude of hj omega would be magnitude of numerator, which is just RC omega, divided by the magnitude of the denominator, which is the real component, LC omega 2, the whole thing to the power of 2, plus R2 C2 omega 2. And the phase of HA omega would be the phase of the numerator is just 90 degrees minus tangent inverse of the imaginary part, which is RC omega divided by 1 minus LC omega to the power of 2. Okay, so let's evaluate this function for different omegas. For low frequencies, say omega equal to 0, the denominator is 1, the numerator is 0. So what that means is that when you go to lower frequencies, none of the input is going to pass through your circuit. Let's see if we could intuitively realize that. Well, for low frequencies, we know that the capacitor is an open circuit, so there's no current passing and the output would be 0. So that was easy to see even without looking at this function, intuitively speaking. Let's see what happens for high frequencies. So if we replace omega equal to infinity, what happens here is that you have a situation where the order of the denominator as a function of omega is actually omega to the power of 2. Why am I saying that? It's because you have an omega to the power of 2 here, and then omega to the power of 4 comes out and it becomes omega to the power of 2. So overall, this ratio is going to approach 0 because in the numerator you have a function of omega to the power 1, in the denominator you have a function of omega of the order of omega to the power of 2. And therefore, the ratio is going to approach 0 for high frequencies. In other words, high frequencies won't pass through your circuit. Let's see if we could figure that out intuitively. For high frequencies, this is going to become a short circuit, but on the other hand, the inductor is going to become an open circuit. L omega J is the impedance of the inductor. Omega approaching infinity, that's an open circuit. So now if we actually draw this function, you're going to see something of this form. Let's see, it's going to go up, and then it's going to go down. For lower frequencies, why am I saying it's going to go up? Because you can place, put omega something other than 0 or infinity, and you're going to see that the value is going to be something larger than 1. You can actually plot that using a computer, and you see the same thing as well. Therefore, this filter, this frequency selective system, could be called a bandpass filter, because there is basically a band of frequencies that are passing through the system with a high amplitude, and both the lower frequencies and higher frequencies are being rejected. They're not passing through your filter. Now, the same way that we define cutoff frequencies for first order or low pass and high pass filters, we should do the same thing here. Basically, we want to be able to have a metric for what frequencies, generally speaking, passing through the filter, which would then we're going to define it as frequencies, the power of which is going to pass more than half through the circuit, right? So for that, I'm going to first have to find out what the maximum of Hj omega here is. And to do that, basically, generally speaking, whenever you want to maximize a function in mathematical term, you have to take the function, take the derivative, equate that to 0, and you find out what frequency is going to maximize or minimize the function, and then evaluate the function at that point, and you get the maximum. I'm going to show you something here that is relatively easy to do. If you put omega equal to 1 over LC, this becomes 1, and this term completely goes away. And then this right here becomes 1 over L2C2, the two C's go away, so this becomes R2 over L2, comes out of this square root, becomes R over L. Same thing happens here, that becomes R over L, the two R over L's go away, and you get 1 as a result. So at frequency of E equal omega equal 1 over a square root of LC, this particular phenomenon happens where the transfer function actually becomes equal to 1. And if you evaluate the function, you will quickly realize that that is actually the maximum that this function could ever have. Again, you can take the derivative of the function and get to the same result. You do all of that and you get to the same conclusion. This frequency is called the center frequency of the circuit, and actually it has another meaning. This is the resonance frequency of the circuit too. Unloaded resonance frequency of the circuit. Basically, at this frequency, the impedance equivalents of the inductor and the capacitor cancel each other out. So let me quickly discuss that with you and see what's going on. So the impedance of, just focusing on that part of the impedance of L plus C is equal to L omega J plus 1 over C omega J. That's the same thing as L omega J minus J over C omega. That's the same thing as L omega minus 1 over C omega J, right? So if you set omega equal to 1 over a square root of LC in this function right here, these two terms go away and you get an impedance of 0. In other words, L omega minus 1 over c omega equal to 0. That gives you L omega equal to 1 over c omega. That gives you omega 2 is equal to 1 over LC. That gives you omega 1 over square root of LC, at which point the impedance of these two components in series to each other becomes 0. So that becomes a short circuit. That's a very interesting phenomenon called the resonance of these two, at which point, basically for that particular frequency, this node and that node are going to have the same voltage, and that's why all of the signal we are saying is passing through. Okay, so keep that in mind. Now let's move on and try to calculate the cutoff frequencies. So now we know that the maximum is 1. So at cutoff frequencies, we said RC, the magnitude, which is here, that's RC omega c divided by a square root of 1 minus LC omega 2 to the power of 2 plus R omega c. R2C2 omega c to the power of 2 is equal to H max, which is 1 divided by a square root of 2. So if you solve this equation, you're going to get 4 values for omega c. 2 of them are negative, you reject that, and then the other 2 end up being omega c1 and 2, or a square root of R over 2L to the power of 2 plus 1 over LC plus minus R over 2L. And these are the two frequencies at which the magnitude of the output becomes 1 over a square root of the magnitude of the input, or the cutoff frequencies. Now, if you notice, there's something here. So the lower one, the lower frequency, which is this term minus R over 2L, is this one, and the other one is that one. So one of them is higher than the other one. We call them omega C1 and omega C2. There is something here that you can notice. When we were solving the same circuit, if back in when we were discussing second order circuits, this is actually R over 2L is your alpha, is the damping factor, and then this is alpha to the power of 2 plus omega 0 to the power of 2. So these are actually, if you find the zeros or poles of this function, they're going to give you pretty much the same thing, right? And we discussed this. There are the poles of this function end up being the cutoff frequencies for your, the magnitude are going to be the cutoff frequencies for your. You have to, so you have to remove J from that, because that's not, omegas have to be real numbers, right? But nevertheless, this is that there's a relationship between the poles of your HS and your cutoff frequencies that again shows up. Now, one other thing that I have to mention here before moving on to band reject filters is that we can define the concept of bandwidth again. So bandwidth would be range of frequencies that we assume approximately passing through your circuit. That would be omega C2 minus omega C1. And if you do that, that would be R over L for this case. Simply R over L. Okay, now there's one more concept that I wanted to discuss that is something new that we didn't have there was no meaning for it when we were talking the first order low pass and high pass filters, and that's the concept of quality factor. So quality factor is defined, if I can define it somewhere here, quality factor is defined as the center frequency divided by the bandwidth. Now, if you look at this definition, basically when the bandwidth goes down, the quality factor goes up, and vice versa. So this is basically a measure of how sharp your filter is. The sharper your filter is, the higher the Q is going to end up being. And again, for this specific situation, you have 1 over a square root of LC divided by RL, which I'm sure you can simplify. Okay, now for the band reject situation, the same thing that we did before for low pass and high pass, which was focusing on the dual circuit. We can do exactly the same thing here, meaning that we can switch the place of the two components, meaning move R in series and then move L and C in parallel, which is the dual of what we had over there, RLC. So let's see how that's going to play out. HS is equal to, now this impedance, which is 1 over CS plus LS divided by the total impedance, which would be R plus LS plus 1 over CS. Now let's multiply everything by CS again. So that would be LCS2 plus 1. And then in the denominator, you're going to have LCS2 plus RCS plus 1. Now, if I replace S with j omega, this would be hj omega equal to 1 minus LC omega to the power of 2. Same thing that I explained to you before. J omega to the power of 2 becomes minus omega to the power of 2. And in the denominator, you're going to have the same situation, 1 minus LC omega 2 plus RC omega j. Okay, so now you look at the magnitude of hj omega. This becomes 1 minus LC omega 2 divided by square root of the real part to the power of 2, 1 minus LC omega 2 to the power of 2 plus the imaginary R2 C2 omega to the power of 2. And let's just write up the phase as well. So phase of hj omega would be, now the phase here is 0, so then 0 minus tangent inverse of, phase is 0 because this is a real number, as opposed to that where that was an imaginary number, minus tangent inverse of the imaginary RCW over the real, 1 minus LC omega 2. Okay, so let's evaluate this function quickly. For omega equal to 0, this is 1, and that's also 1. So this ratio becomes 1, meaning that all the signal is going to pass through. Why is that? Let's see if intuitively we could conclude that. So for low frequencies, this is an open circuit. The capacitor is no current, and therefore these two voltages are going to be the same. This is a good sanity check for the calculation that we did. Now for high frequencies, what happens is that this one has omega to the power of 4 comes out, and it's going to have omega to the power of 2. Now, therefore, both top and the bottom are going to have omega to the power of 2. But more importantly, this term right here is the value of this term is much larger than this value at omega, very large omegas, for a obvious reason. This one has omega to the power of 4 in it. So I can actually neglect or ignore this with respect to this. The whole thing comes out, and ratio becomes 1 again. So for very high frequencies, again, you're going to have the same value as low frequencies, and that's 1. So magnitude of hj omega, it starts at 1, and it goes down, and then it comes back again and approaches 1 again. So starting at 1, approaching 1. And in the middle, something happens that we're going to see quickly. So let's evaluate this function at that frequency right there, 1 over LC. If you do that, you can immediately see this becomes a 0. So this value of angular frequency is going to make h magnitude of 8j omega to go down to 0. So if I want to be true to that, this actually have to go all the way down to 0 and then come back up. That is frequency of omega equal to 1 over LC. If you do the same thing that we did before, basically trying to understand what is going on. This is the same thing that we discussed, the resonance frequency for L and C. In other words, this is the frequency at which point this impedance becomes 0, so this is a short circuit. Then again, this would have been something that we could have intuitively realized. And if you do the same thing to calculate the cutoff frequencies, you're going to actually end up getting exactly the same thing too. Doing exactly the same thing, H max being 1 again, and you get the same results. So the cutoff frequencies would be the same thing as well. This is the frequencies at which you get 1 over square root of 2. Now, at this point, the name band reject should make sense to you, because what we are saying is that there's a band of frequencies, omega C1 to omega C2, that inside which or within which this band, within this band of frequencies, approximately the signal gets rejected, meaning none of it is passing. It's actually only half of it getting rejected, more than half of it is getting rejected, but you approximate that and you say within this range the frequencies don't pass through. Obviously at certain frequency none of it passes through, but generally within this range less than half of it is passing through, and therefore the name band reject. You can define the same concept of a bandwidth again, which would be omega C1 minus omega C2, the same way as well. And the same discussion that we had about the first order low pass and band pass filter, you can have that here too. You can have band pass and band reject filters that have higher orders, meaning that the denominator could have could be a function of S to higher powers, higher than 2, which is these systems are second order. And if you do that, you're going to get sharper roll off, and the filter is going to get closer to what an ideal filter would have looked like. So an ideal band pass filter would look like this. Omega C1 and omega C2. Anything before that is 0, and then all of a sudden it goes and reaches a constant value of say 1, and then an omega C2 and above, again it goes back to 0. You will never get that, but you can keep increasing the order of your filter and get closer and closer to this, so that you can basically see situations where this goes up and kind of ripples and then comes back down like that. The number of these ripples that you have here, ups and downs, really is a function of the order of the transfer function for the system that you have, and every time that you want to increase the transfer function, you have to increase the number of energy conserving components in your circuit. These kind of discussions are more advanced, and you can normally see those kind of discussions in classes or courses where the focus is on analyzing filters, designing filters, and such courses exist in most electrical and computer engineering departments. Thank you very much for your attention. and we're almost done with the concept of filters. There are a few things that I'm going to discuss in the last lecture, and we then move on. Thank you.